This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
But I'll sort of add more information as I go along. But there's a lot of stuff that is on the slides is sort of self-explanatory. But I just want to emphasize some of these important points. Like for example, how many of you seen this bridge? Okay, anybody been to Scotland, like Edinburgh or no? No, you guys don't travel a lot. No? Yeah. Not to Scotland. No reason. Well, actually, I stayed in Scotland for almost 9 years. Yeah, I was doing my studies there. So there's one particular bridge called the Forth Rail Bridge, right? It's somewhere between Glasgow and Edinburgh. Now, it's amazing structure. It's really amazing. If you ever have a chance to, they say the bridge is so huge, right? The folks start painting here. By the time they finish painting, they have to start again because the paint from where they started has corroded. So yeah, it's that huge. And you may not think when you see it like that, you don't think it's big, but you can see the size of the train, right? On the bridge, and this is just the start of it. So it's a huge bridge. Now there's a reason why it was so big, because what happened was this bridge was built in the 1800s. So they were building this bridge, and as they were building it, they were planning it, there was another bridge, right, that collapsed. Okay, and the engineer that was actually building this bridge was responsible for that bridge that was collapsed in the Tay, another bay. And actually, it's a very sad story because eventually he went into depression, and he never finished this bridge, and he died actually. I don't know exactly how he died, but he died, and because there was an inquiry and so forth. So one of the things that he didn't take into consideration was in Scotland the wind are very strong. So what happened was that the weather and things like that caused the whole bridge to collapse. So when the second engineer took over the job in constructing this bridge, I mean, he didn't leave anything to chances, right? So, he built this huge bridge, right? Just to make sure that, nothing will make it collapse. But of course, today, if you go and look at, suspension bridges, and they're really slim, they are very optimized, and they can do what they can do. So it's nothing like this. Now, the reason why I tell you this story, you may be wondering why, okay, is that sometimes we don't think about it, but you as an engineer, okay, structure is very important. All right? The reason I say structure is very important because there's a reason why this bridge is built in the way it's built, because it has to function, right? It has to take function. The function is that trains got to go through. There's a lot of vibration. There's wind. So therefore, the structure has to serve the function. Now, a lot of time, right? As bioengineers or biomedical engineers, we sort of assume that it is a given, the structure and the function is a given, right? So I give you a good example. Now, if you look at tissue engineering, okay, you make scaffolds, right? Okay, what is the thing that you think about when you make scaffolds? Most of the time we are thinking whether the cells will grow, right? But do you actually think that, whatever you put this thing in will serve the structure? Let's say, for example, if you're going to put the scaffold into bone, for example, right, into bone, okay, right, then you say, oh, I'm going to grow osteocytes, I'm going to grow bone cells, and then I'm going to plug it into, right, and you just assume that structurally it's fine, okay, and then you think about people who make orthopedic implants, okay, what do they use? They didn't use soft, cushy plastic, right? They were using titanium, they were using stainless steel, right? They were going to that other extreme just to make sure that, because all they care at that point in time when you're making implant is that it can take the load. So when you're designing, say, tissue engineering, for bone, right? Do you actually consider that you just assume that the cells will make bone and then the bone will be strong enough? But does that actually happen? We all don't know. So I really, really encourage you to think a little bit more, because biomaterials is a little bit more complex. So there's a very nice article, okay, which is this one here. All right, okay. Now, I don't know whether, yeah. So tissue engineering, okay, all right. So they talk about first, okay, the in vivo stress strain history, second, the mechanical properties, third, the mechanical properties selected must be prioritized, fourth, standards where how you repair after surgery, fifth, the physical factors, all right, and then finally, the cell matrix implant, whether they can be stimulated and grow in biome. So if you look at it, the function of tissue engineers role in biomechanics, right? The first few priorities, they're all talking about mechanical strain, mechanical forces, right? So you got to think a little bit about it, okay? So don't always think that, whether the cells will grow, all right? Okay? So that's the story of my bridge, all right? Okay, now I'm going to talk to you about hard tissue first, okay? Oh my goodness, I can't find my mouse. Okay, so today we'll be talking about structural properties, okay, at the macro and micro level. So a little bit about mechanical properties of bone and also the Wolff's law, right, about bone remodeling. Now, so bone, the important thing for you to take note is, the bone structural properties, okay? So of course, bone is made up of connective tissues and, there are a lot of calcium phosphate, you can read that one. But I'd like you to pay attention to this bit here. Okay, the anisotropy, the non-homogeneity, the non-linear, very complex, thermorheologically, and then viscoelastic. Now, how many of you know, like, for example, if I say non-homogeneous, do you know what it means? You guys are engineers, you should know, right? Non-homogeneous? Yeah, okay. It looks different, okay. All right. Anisotropy? Anything? You know what's isotropic? Anisotropic? Yeah. So sometimes, when you talk about isotropic material, the easiest is, let's say you got a piece of square, two-dimensional material. When you pull this way, now you expect the top bit to shrink, right? Okay. And the amount of displacement here is, related to the amount of displacement here. So being isotropic. But if it's, in fact, it's the same. If it's anisotropic, you can pull here, it shrink a little bit. No, not as much, so it's different direction. Okay? Right. Now, then non-linear. All right, you must know non-linear. Okay. So if I were to draw this graph, it doesn't matter, some axis here, okay, so y-axis and x-axis. Say if I have load, and then I have displacement. Okay, so if I take a material and I pull it up here, okay, I'll calculate the load and then, how much has it displaced. So this is my displacement. Okay, so there is a relationship between the two, right? Okay, the more I want to displace, the higher the load will go, right? So in other words, okay, my displacement increase, my load also increase. Okay, if it's a linear, the relationship is, you'll get a straight line. Okay, if it's non-linear, very simply, it's just either going to be curve here or curve here, right? Okay, so in other words, if you pull, okay, displacement can be huge, all right? So if I were to draw a graph like this, did you see the mechanical test that's being performed in the lab? Right? So let's say, okay, you got displacement again, you got load. So if I apply a small load, okay, right, I get a large displacement. And then, and then maybe the displacement become much smaller, okay, right? But, you increase your load. All right, so this becomes nonlinear. Now, so viscoelastic I'll explain later, but just bear in mind, bone, soft tissue, right, they're all like that. they're all anisotropic, non-homogeneous, non-linear, and then viscoelastic. I'll talk a little bit about that one. Okay, so in other words, when you have materials like that, okay, it's actually an engineering nightmare. It is really very difficult to deal with because it's very difficult to predict, okay? It's very difficult to describe mathematically, and it's very complex, okay? So you always think that life, you like to be linear, you know? The moment it becomes non-linear, it's a bit difficult to maintain. Okay, now, so here I'm going to tell you a little bit about the structure that makes it a little bit non-linear. So when you look at bone, there are two components, two very sort of evident type components. The first one, of course, is the cancellous bone. The other one is a cortical bone. Now, the difference between the two is quite straightforward, so I'll just skip this one. Right, you got like almost a hard bone outside, and then you got this, you know, a little bit porous bones inside. Okay? All right. So next time when you have your Kentucky Fried Chicken, all right, you know, bite into the bone and have a look at it. Okay, all right. It's really fun, you know. Have a look at it. Okay, and then you can see your cancellous bone. You can see your cortical bone structure. Okay, all right. I know some of you would just eat the bone. Okay, right. Okay, right. So have a look at that now. So because the structure is a bit complex, then of course you've got all your, you know, canals, your blood vessels, and then embedded inside your cells. Okay. Now, there's some diseases that that cause bone problems. So one of which, of course, is osteoporosis. Okay. So if you look at the two micrographs, so these are microstructure where the cancellous bone is, where you get all the porous bone. You can see the first one is very, you know, nice and healthy. The second one, you start to see that there are big holes in it, okay? Right, so the cancellous bone starts to disappear. So this is what we call osteoporotic bone. So we do a lot of cadaver studies, right? Or sometimes you talk to surgeons, okay? You know, orthopedic surgeons. They could open up, you know, to do surgery. Literally, they could put their finger and poke into the bone, right? It can be that soft, okay? So we do a lot of cadaver work. Sometimes we got very specimens that are from very elderly, and then, you know, the bone is just really soft, very spongy and soft. Okay? Now, so it is a big problem, osteoporosis. Now, so here are the different structure, okay, right from the smallest, you know, to your crystals, okay, right? So you can read this one. Now, so this is important, right? So quite often I ask you in exam, okay, describe, you know, bone, right, mechanical properties. So I like to say, oh, bone is non-homogeneous material, right? Bone is anisotropic, and bone is viscoelastic or time-dependent. Okay. Now this is important because, you know, if you are an engineer, right, when you are given a material, right, the first thing you want to ask is, oh, do I know the material properties? Can I describe it mathematically? Okay. Now, same. So with biological materials, it's a lot more complex. Now, the interesting thing about engineering is that engineers are a little bit like control freak, I would call them. Okay. So they want to make sure that they can control the system that they are dealing with. So, you know, if you ask an engineer to solve a problem, they will want to make sure that, you know, they can control everything. Right, but when you deal with biomedical problems, there are a lot of boundary conditions that you can't control. Right, for example, you can't control, you know, all the biological processes, but you have to introduce something engineering into it. So that makes it more challenging. So you work within a certain set of boundary. Okay, so this case, the boundary is really the material properties of, you know, your biological materials. So you're going to put a material that you can control, which is a synthetic material, your polymer, your fibers, your metals, okay, into, you know, a system like this. Okay. Now, so the stress strain curve for bone looks like this. Okay. So when you load it, okay, you will start to see. Okay. So we are talking about if you take a bone, right, and then you start to pull it, or even compress it, Okay, you see that, you know, the stress and the strain. Now, I assume that, so in your lecture notes, right, there is a simple Ench mechanics, you know, concepts. So I assume that all of you done physics, right? No? Yeah? Okay. So you will know what is stress, what is strain, right? So I don't have to explain. Now, so when you start loading, you get, you know, something fairly linear, and then it goes into plastic, right? And then it breaks. Okay. So you get this kind of, you know, loading conditions. Now, the one thing that because of the viscoelastic, so we talk about viscoelasticity, okay, the viscoelastic nature. Now, the easiest way to understand viscoelasticity, I always tell students that, you know, blue tack, you know what blue tack is? This sticky, rubbery stuff that you stick on the wall and then you stick in it. Right. Now, if you, next time you have blue tack, you take blue tack, right, you put it into a ball, and then you pinch the two ends, you start pulling them apart, okay? Now, you pull it slowly, all right? Okay, pull it slowly. Now, just feel how is it like to pull it slowly. And then you make it back in the ball, and then now you yank it quickly, right? Now, you will feel immediately, when you pull it slowly, you don't need a lot of force to pull it, right? You'll be quite happy pulling it. But if you pull it very quickly, suddenly the material seems to be much stronger, right? Now, what is happening is that the material is rate dependent. In other words, the faster you pull it, okay, the stronger the material is. Okay, so viscoelastic material is very much like this. So if you look at the top graph where you've got stress and strain, now if you take a bone, in other words, if I strap you in a torturing device and then I crank you up slowly, you know, and start pulling your bone, I don't need a lot of load, right? I could pull you, so it will be slow loading. Now, if I were to pull you quickly, right, I need a lot of force, all right? Then that will be fast loading. Okay, so your soft tissue, your bone, they all behave like that because of the viscoelastic nature of the material. Okay, all right, okay, so that's your, you know, viscoelastic nature of bone. Now, so when you look at material properties of bone, people have, you know, we try to simplify things. Engineers always simplify things. So eventually what we say that, oh, you know, it looks pretty straight. Okay, though it's non-linear, we draw a gradient, right? And then of course, if you take stress divided by strain, okay, you got this thing called Young's modulus, which is E, all right? So the Young's modulus, okay, or the ultimate, okay, this is the bottom one. So for longitudinal and transverse, they are different. So in other words, if I take a bone, this is your bone, okay? So let's say take the femur bone, right? So if you take longitudinal, this direction, right, and then transverse like that, okay, cut it like that, all right? You take this bone and you pull it like that, and you take this bone and you pull it like that, you get different strength, okay? You get different strength. So you can see that the modulus changes from 17 gigapascal to 11.5 gigapascal. And then shear, if you twist it, you know, you get about, you know, 3.3 gigapascal modulus. And then the strength, the ultimate strength, tension, compression, shear, right? And then transverse tension and compression. So quite interestingly, you see that when you take bone and you pull it, right, you get the ultimate strength. So the breaking strength will be about 133 megapascal. But if you compressed it, okay, it is 193. So bone are typically stronger under compression, which is good, right? Because we have gravity, right? Understanding. So I like my bone to be stronger, you know, under compression. But you may say, since when is your bone under tension? Have you ever thought about it? Like, you know, how often do you get bone under tension? Huh? Rock climbing, hanging, yeah. But let me tell honestly, your bone is always under tension. Okay, now because, you know, don't forget, right, we are never living, you know, I'm never standing so, my body is never like perfectly aligned perpendicular to the floor, right? I'm always, you know, experiencing bending. Okay, so bending is the key load that you have to think about. So when you have something that is bent, you're always going to get compression and tension. Right? Take for example, if I have a shaft, okay, if I bend it, right? If I bend it like that, okay, so my materials will go, say, if I bend it like that. This part of my bone will be under compression, right? This part of my bone will be under tension, okay? Right, so your bone is always under compression or tension, okay? Or at the same time, you know, depends. So because you're always subject to bending. Right, now, so the other thing is a very interesting thing that you see. So, okay, now here is a comparison between cancellous bone and cortical bone. All right. So if you start pulling cortical bone, you know, if you separate cortical bone, which is your very tough bone outside, okay, the strength is a lot higher than your cancellous bone. Okay. Now this is compression. So one of the very interesting thing about compression is that if you take cancellous bone, right, you compress it. So this is your cancellous bone. You got lots of, you know, matrix here. Once you compress it, all this little trabecula will break, okay, and then they become more and more compact. All right. So eventually, you know, they become like a very compact bone, which is why you see, you know, your loading sort of flattens out, okay, and then it goes up. It even goes up and becomes stronger, right? Because you know it's like a compact bone, so you get that. But that scenario is simply because your bone is, you know, breaking. Then dry bone and wet bone, again, you got different, you know, characteristic. So bear in mind when you test bone. So during all our testing, we always make sure that we make sure the bone is wet, you know, under more physiological. So this is where, you know, I show you how bone is under compression and tension, and then this is some of the typical fracture that can happen in long bones, right? Pure tensile, pure compression, you get that line, torsion, bending, but typically you're going to get this kind of combined loading. All right? Anybody has broken bones before? No? You guys are all very safe, you know. Yeah, no, like, you know. Okay, now, very quickly, just want to talk to you about Wolff's law. So back in the, I think this is 1800s, right? So Wolff described that, you know, when you look at the trabecular structure in bone, they sort of align to your principal stress or principal strain. You know, so in other words, your bone remodel. We know that bone is alive, right? It changes shape. So what it does, it changes its shape, especially the trabecular structure, to, you know, try and maximize or reduces the amount of load onto the bone. Okay, so your bone is always remodeling. Now, there's a lot of very interesting work around bone remodeling and modeling, okay? Right. So just be aware of Wolff's law. Okay, these are some of the mechanical tests that we've done on bone. I will upload 2 papers, okay, two research papers. Okay, so this is one where we look at the shock absorption ability of articular cartilage subchondral bone under impact compression. So you can look at it. So what we did was So we have a bone, a cartilage bone like this, and then we indent it, we impact it, and we have a microscope and a high-speed camera, and then we look at, you know, the displacement of cartilage and bone. Right, there's a very nice video that shows, you know, cartilage and bone, and then we could capture when it fractures, and then we do finite element modeling, you know, and then look at how bone fractures. Okay, so this is one of the work that we did, one of my students, and then the other one is so I'll upload these papers. The other one is looking at, you know, dynamic compressive mechanical properties of cancellous bone. This is an old paper. We are looking at the spine, and then so we took bone, so you can see the cancellous bone in the spine. Its cortical section is very thin, right? And then we do some impact studies and look at the compressive strength. Okay? So when you look at these graphs, you will understand them. Okay? All right? Okay, have a look at these two papers. Now, very quickly, we will go to soft tissue. Okay, so soft tissue, we're going to be talking about connective tissue mainly. Okay, I will not go into muscle tissue or nervous tissue, right? Mainly connective tissue. So connective tissue could be skin, ligaments, you know, and so forth. All right. So skin, all of you are familiar with skin, so I will not go into. So I want to basically. I want to focus on the mechanical properties because this is a material class. So you can learn, there's lots of stuff in skin, but the physiology. But this is a material class. Just focus on the material, the materials component. Now, so there are a couple of fibers. Okay, don't worry about this. This one here. There are a couple of fibers that give strength to your connective tissue. Okay. Right, and there are two particular fibers that I'd like you to pay attention to. It's the collagen fibers and the elastic fibers. So when you take, say, any connective tissue or skin, or for example, you see something like this. You got your collagen fibers, right? You got all these very thin elastin fibers, okay? And then you got your reticulum fibers as well, reticular fibers. But you got all these big cells like, you know, your big fat cells. Some of us have more, you know, some of us less. Okay, your macrophages, okay, right. But there are two fibers that I want you to pay attention, which is the collagen fibers, and which is a big, thick, fat one, and then the elastic fibers, which are the thin fibers. Okay, now, so from the two names, right, what can you guess? Elastic fibers is very elastic, okay, all right, and then collagen fibers are, you know, pretty strong, right, they are pretty tough. Okay, now, and now you know, right, you can make yourself look nicer if you put collagen in, you know, yeah, you can inject here, maybe here, you know, right, so it gives you firmness, okay, right, okay, right. Now, so I won't go into this, right, I want to talk about, so all this is talking about the microstructures, this one here. Now, this is very important. Okay, now look here, okay, in this table, you have tissue, okay? So we show you a couple of examples. So you got skin tissue, lung tissue, aorta, you know, ligaments, tendon, or even the liver, right? They all have elastin fiber and collagen fibers. But I'd like you to focus on sort of the load-bearing type tissue. Okay, look at skin. Okay, you got about, you know, 0.6 to 2.1% of dry weight, okay, of elastin fibers. And a lot of collagen, right, 71 point, which is good news, right? So, you know, we don't have drooping faces, right? Okay? So you got more collagen there. Now, if you look at ligament is very interesting, right? 74% elastin, okay? Right, and then 17% collagen. Okay, and then you look at tendon, right? 4.4% elastin and 86% collagen. Almost the opposite, right? Can you guess why? So let's talk about ligaments and tendon, right? So what do you think ligaments do? So where do you find ligaments? You say again? Oh, no. That's tendon. Yeah. So muscles attachment to bone is tendon, right? Yeah. Ligament will be, yeah, bone to bone. Okay, so the good example is when you look at your spine, you know, two bone segments, you got ligaments, lots of ligaments, because they connect bone to bone. Okay. Now, so when you look at, you know, let's look at the spine. Okay, you bend, you know, you do all sorts of action. Okay, so you like it to be very elastic because, right, if it's very tough, what will happen? It may rip your bone off, right? Okay? right? Because you need it to be elastic. So let's say suddenly, I was walking down the stairs, I missed a step, oh boom, backache, right? But nothing happens because my ligaments takes all the, all the shock, is able to, make sure that whatever bending I have, doesn't break. But what about tendon? Okay. What if tendon is very elastic? There's no purpose, right? Right? Because that's why I always tell students this. If I think about moving my arm, if my tendon is really elastic, right? After I think about moving my arm, it takes a few seconds, right? And then you slap yourself, that kind of. So you don't need that, right? You don't need that. So somehow, by nature, as we progress in life, things change. So each of this has its function, all right? Okay. Now, so what we like to do is then show you. I'll show you this. So this is very important because this is how you, as an engineer, you say it's collagen, tendon. So if you are a chemical engineer, you say, oh, collagen is, these are the molecules and stuff like that. But when we talk about engineers, we are interested in the stress-strain plot. We are interested because we are interested in the mechanical properties. This is a terrible graph. If my colleague sees it, they'll throw me out because the axis has got nothing. Okay, but if you can write it, so assuming that you got load displacement, right, or load and strain, so you got like 0% strain, 5% strain, 10% strain, right? So you can see elastic fibers can actually be stretched 2 times, its own length, right? Before it breaks. Whereas for collagen fibers, you stretch about 10% strain, it's just gonna break. Okay, right now, and you can see that if you have the y-axis, if you plot them together, what happens is this one you take a little bit of load, you can stretch it really far. Okay, whereas that one you need quite a lot of strength to pull it apart. So when I ask you to describe, the mechanical properties of collagen and elastin fibers, please just draw these 2 graphs. Okay, you'll get your marks. All right, it's very easy. Because it's, we like diagrams like this. It will tell us exactly what, we're describing. Okay, so this is some description. All right, there's some description of the structure. Now, here is the more interesting bit about, about biology. I mean, it's just very interesting, surprising as well. Now, when you look at skin, tendon, and ligament, right, I'm going to show you this graph here before we go back here. Yeah. Okay. Now, so if you look at skin, tendon, and ligament, tendon is mainly made up of collagen, right? So when you need a lot of strength to pull it, even for a short amount of distance, right? Okay, so you need a lot of strength. So it goes all the way up. So you'll always be sitting in this part of the graph. Okay. Now, when you look at skin, okay, right, and you look at ligament, okay, they are sitting right around, about the same order, okay. Now, they are sitting around, but I'm curious, why are they behaving like that? Okay, why do I say they behave like that? Because the amount of collagen and the amount of elastin in skin and ligament, right, go back here. Look, okay, skin, all right, 2.1, collagen, 71.9. And then look at tendon, 4.4 and 86. Shouldn't skin be sitting next to tendon? You know what I'm trying to say? All right. Why do you think it is not? It is more like a ligament. It's interesting, right? So, we have tendon sitting right around here. Okay, ligament, we understand, is very elastic, okay? Because there's a lot of elastin fibers there, okay? Right. But skin, instead of sitting here, is actually very elastic, Actually, skin is really elastic, you know, right? Okay, right. So you always wonder why, right? Why? Okay, let me tell you why, right? The why is really simply the way it is structured. Okay? What happens is if you look at the collagen fibers in skin, right, they are sort of like spaghetti. They're not aligned at all. Okay, they're not aligned. So if you take a piece of skin and you start pulling it, what really happens is the collagen fibers will all be, you know, straightened to the direction of the pull. And then when you get them all straightened to the direction of pull, so what will happen is, you know, all these things that is happening here, you don't need a lot of load to straighten the spaghetti, right? You know, okay? Until it all becomes straight, it suddenly becomes like, you know, your tendon, and it just shoots up like that. Okay? Right. So if you want to explain why the stress-strain curve of, say, a skin is very similar to that of a ligament, right, it is because of the way they're oriented. All right. And then if you look at the collagen fibers in tendon, right, they're all straight. Okay, the elastin fibers are all over. All right. And then for ligaments, you know, all the elastin fibers are all straight. So, you know, that's why the moment you pull it, it's all very elastic. Okay? Okay? So now you understand that, okay, collagen fibers roll. If I repeat, collagen fiber very tough, elastic very soft. Then the amount of collagen and elastin fibers determine how the tissue behave. So different tissue has different composition, different amount. And then their orientation is also different. All right. So you get that mixture. Any questions on that? Good? All good? All right? It's quite interesting, right? Okay. Now, so I'm not going to go through this. So this one you saw, okay? That's what we are describing here. So, you know, you start pulling it, becomes straight, and therefore goes straight. So I quite often ask questions like this because it's a nice question, you know, easy to ask. All right, in an exam says, oh, you know, tendon, skin, ligament, describe the behavior, and things like that. Okay? And then these are some, you know, pictures. Now, coming back to the viscoelastic behavior, right, and time-dependent behavior, this slide basically explains that. So exactly the same as bone. So there's this creep effect as well, right? If you take, say, you know, a tissue, you pull it, right? Say you apply, you know, 2 kilograms, you stretch it. Okay, the moment you stretch it, you stop, okay, and then you go and have a cup of coffee and come back. You didn't increase the load. It's still 2 kilograms, but it has become longer, okay? Because there's time dependency. It sort of creeps slowly, okay? All right. Any questions around that? Good. Okay. Right. So again, you know, soft tissue are very nonlinear. Okay. Now, in the more advanced classes, what I then try to do is I try to, you know, provide you equations to fit this curve. All right. To try and come out with a constitutive equation. Now, to develop a constitutive equation for any biological tissue is actually very challenging and very fun as well. All right. Now, as engineers, we like to describe everything mathematically. Now, if you can describe it, then you can put it into your models. You can, you know, put it into your equations to calculate, to predict. You know. So one of the challenges, even up to today, you know, we are all still trying to find the best fit. You hear things like, you know, linear elastic model, nonlinear elastic model, hyperelastic model, you know, triphasic, biphasic model. There are lots of this kind of models. So there's a lot of people proposing models to describe the behavior of soft tissue. All right? Okay? So the whole bioengineering field started very much in trying to, you know, characterize, there's a very famous professor called Y.C. Feng. He's going to celebrate his 100 years old soon. Yeah. They call him the father of modern biomechanics. So he started his work around artery vessels, and he was basically trying to characterize these material properties. Yeah. Okay, the other very interesting thing is what we call hysteresis. Okay, now, so this is again very common for biological materials. Now, I always say you need to know biological materials because you're gonna put things into the body, and you can't pick and choose, right? So you got to work with it. Now, one of the things that you do is that when you load a material, let's say if it's a linear elastic material, like say a piece of steel, right? You pull it before it breaks, you know, go into plastic. You unload it, it will always unload back in the same line, all right? Okay, but for non-linear elastic material, or in case of tissue, non-homogeneous, you load it, it's non-linear, okay? And then you unload it, it will never follow back the same line. It will sort of drop. And then you got this creep effect, which may eventually go back to this point, but it will take some time. But if you load it again, right, it will shift, right? And then you load it again, it will shift. It will keep shifting. And then this shift becomes smaller and smaller, and then it will start to, you know, coincide. Okay? So this is what we call preconditioning. So typically when we do mechanical tests on any soft tissue, we will load cyclically until, you know, you achieve this line, okay, at a low load, right? And then you start to load it all the way until it fails. And then you have this nice line to then characterize your tissue. All right? So the precondition first, and then you move on to, you know, do your test. Okay? So if you're asked to do mechanical tests, always think about, did you do preconditioning? Okay. Any questions there? No? Good? Oh, good. Now, one more thing is everything to me is interesting, okay? But have you ever heard of this thing called Langer's line? I saw somebody nod. Okay. Did you have plastic surgery on your face? No, just kidding. Yeah. Anybody have heard of Langer's line? It's a very interesting concept. Yeah. I saw some head nodding. So what Langer's did was it was quite interesting. He took a cadaver, right? He take a sort of an ice pick, okay, and then he start to, you know. Wait a minute. Have some of you actually attended this lecture before? No. No. Yes. Who is from biomat? So you guys attended this lecture before, right? From that FIB thing, right? Yeah. Oh my goodness. It's always very embarrassing teaching the same thing twice. Yeah, if you're from biomet, but it's important. It's good for a reminder. Okay, so don't tell them. Now, so what they did was he took a body. And what he did was he taken a sort of a cutter, right? He cut into the body. It's a circular cutter. So he cut into the body, right? And then the moment he cut into the body, so first of all, you got your, okay, so imagine this is a leg, right? So you take a cutter, you cut into the body, okay, and then you lift it out. So you've taken the skin out, right? And he observed something very interestingly. Once he take it out, okay, the circle is no more a circle. Okay, the moment he takes it out, it's no more a circle. It becomes sort of like, sometimes it becomes over this side like that, okay, and then sometimes it becomes over like that. All right? Now, so what do you think is happening here? So those guys, you can't answer that, right? So what do you think is happening here? There's something happening here. Talk about engineering, right? Don't think engineering, okay? There is a stress component. There's a force there, right? That changes the shape. There's a pre-stress, okay? A pre-stress. In other words, your body has some sort of pre-stress in it. Okay, so what happens is after you cut it, right, circle, okay, and then it becomes over. In other words, the body, the skin is somehow pulling this direction, okay? Right, so he does that. So he basically, took the body and cut lots of holes, all right? And then the nice thing he did was quite interestingly, so he cut them. So now, so you got another oval shape here, and then, you know, he starts to draw lines, longitudinal lines, okay? And then he then called this Langer's line. So you end up with lines like this. So you see the direction? Okay, now why was he so interested in that? Because assuming this is your Langer's line, okay? So your Langer's line is showing like that, all right? So you get all these oval shapes, right? Okay. So like the neck there. Now, if you're a surgeon, right, if you're doing plastic surgery, anything like that, okay, how would you cut? You will cut along the line, right? Okay, you will not going to like that, right? Okay, because the moment you do that, okay, there's a pre-stress that will start opening up this wound. Okay, all right. So that's why, you know, when he did this, it was quite interesting, quite amazing, you know, to think like that, and such to notice that. So you will create a, you know, a smaller wound, that's for sure, and you make sure that, you know, you're in much better shape after the surgery. Okay, all right. So next time, if you go for plastic surgery, ask the surgeon, do you know Langer's line first, right? Okay. If he doesn't know, better don't let him cut you out. Okay, right. Now, so I emphasize again, it is important, in your term paper, okay, to get a good understanding, okay, of biological materials. Because always remember, so there are two things that we've been trying to get you to know in this course. One is that, you know, the biological response, all right, and of course the mechanical response of the biological materials. So we will be putting in things that will touch blood, for example. Okay, no matter how, I think it's very difficult to put something into the body and not having it contact with blood. Because somehow, you know, there's just blood everywhere in your body, which is a good thing, right? You want that, all right? So you can't avoid that. So what happens if blood touches your synthetic material, your fibers, you know? And then the next thing is we want you to understand that if you are especially working on load-bearing stuff, okay, we want you to have a good understanding of mechanical, you know, properties of tissue, okay, when you put it into the body, okay? Any question? All right, yeah.
How concerned should we be with muscle attachment or
Muscle attachment. Yeah, so it depends what we are trying to do, right? Yeah, so muscle attachment is important because muscles has to do with function, right? So, and then the function of muscles is, of course, you know, moving your body. Now, so if you are doing something to the body, right? Say, like, for example, if you're putting an implant in the jaw, you like to make sure that you're not cutting away on muscles, because all muscles has a function, right? So very often, if the surgeon has to cut, right, they will try to reattach it again, because they do heal, right? They will reattach again. So there's a technique called myodesist or myoplasty, right? So if you look at the most obvious cases, let's say, you know, you have a leg, right? This is your knee joint, you know, and then let's say, you know, the surgeon is doing an amputation, right? So this is your bone, your femur bone, okay, right? He's going to cut it here. So you got lots of muscles, right? So what do you do with those muscles? So sometimes surgeons, what they do is they'll attach the muscle to another muscle, right? They call it myoplastic, right? Or they can attach the muscle onto the bone, right? So that when you contract those muscles, okay, your bone actually moves, right? So you still give you the mobility. If you don't attach it, right? If you don't attach it, what will happen? Right? If you leave it hanging like that, you contract it, these muscles will just shorten, okay, and nothing happens. Okay? So in the old days, when they do amputation, it's like a butcher, you know, chop, right, and then they leave everything. So you totally lost the function of the limb. Right? But nowadays, you know, you're really recreating another limb, even though you have to take part of the limb off. Yeah, there's some. I was in a conference just recently. There's a group, very nice work they did. So this is really something that we've been thinking a lot about as well. So if you put an artificial limb, so you got an anchor joint, right? Okay. Now, quite interestingly, when amputees, when they cut when the legs is amputated, right? Have you heard of phantom limbs? Right, I see. I heard phantom. So sometimes you ask the amputee, can you move your toes? They say, yeah, I'm moving my toes now, but there's no toes, right? Because the leg has been taken off. But the pathways are still there, right? They're actually moving the toes. So there's a research group in MIT, that Hugh Hear's group, was really quite amazing. Interesting. They took those signals, right, and then they take those signals like moving the anchor, right, and then they use that signal to control the anchor. Right. So now, when you walk, we don't think about it, but we are actually, putting load on our anchor, right? Okay, stiffening our joints and things like that. So they actually get the amputee to relearn, and then they start to feel that, oh yeah, I can move my anchor just by thinking about it. And it's not like they connect the nerves or anything. They just manage to find the signals, right? The amputee has been using all these years to move the anchor and tap that signal out. These are, EMG signals, right? Myo signals, okay? So there is a need to do what they call, you can actually move nerves around, okay? So there's a group up in Monash that does quite a lot of those work. They go into the surgery, they recraft the whole residual limb. They find the nerves, and then they reattach the nerves to a point where, they activate certain muscles, and then they put an electrode outside the skin there. And then you get amplified signals, and then they can take the amplified signals and then control. Because some of these nerves are deep into the muscle, you can't find them. Very interesting stuff. Yeah, there's lots of. You're in a fantastic area. Just like I just wish that you have 6 years here that I could teach you more stuff. Yeah, it's actually very tough because you have to be a mechanical, electrical, civil, or whatever engineers to know everything, right? Yeah, but I always tell students who are in biomedical field, you got to think beyond. You are not trying to be a mechanical engineer. You're not trying to be a chemical engineer, right? Yeah, a chemical engineer can be a biomedical engineer, but they do a different. But you are trained a little bit different. All right. So I think don't always think like you are going for the same job. Yeah, think a little bit bigger. Yeah, you have to market yourself a little bit differently. Yeah. We can talk about that another time. It's Friday. I'm so glad you're here in the first place. Okay, I'll see you. Have a good weekend. Yeah.
We got two ideas.
Let me just off this first.